We continue with Welington Silva speaking on the geometry of horseshoes in higher dimensions.
Obrigado. Bom, so this is a joint work with Google, and I will talk about the geometry of horseshoes. Would like to emphasize that this kind of description of the geometry of horseshoes we will give here is intimately related to fractal dimension, and it also gives us some dynamical features. So in order to give a motivation, I would like to talk about this topic first in dimension 2. Then I will introduce our work, which is the geometry of horseshoes in dimension higher than 2. So I would like to talk about Palis-Balzan's homoclinic bifurcation. And it is the following. You have a horseshoe here in dimension 2, and you have a homoclinic tangent associated to a fixed point here. And this bifurcation is such that the stable foliation cross the unstable foliation with positive speed. And Palis-Balzan and Moreira and Yoccoz, they have some results which relate the frequency of hyperbolas of the maximum invariant set of the horseshoe and the orbit of the homoclinic tangents with the fractal dimension of the horseshoe. And this fractal dimension will be the house of dimension or limit capacity. To talk about this result, I would like to point out the relation of intersection of Cantor sets with the possibility of having hyperbolas or tangencies between the stable and unstable manifold of the horseshoe. So the red is the stable manifold of the horseshoe, and the blue is the unstable manifold. And you have foliation, and the stable and unstable foliation there. And the stable and unstable foliation gives rise to this line of tangents between them. And then you can have the intersection, the homoclinic intersection, if the blue touch the red in this line of tangents. But these blues and reds, they are Cantor sets in dimension 1. And there is this remark and this result about Cantor sets in dimension 1, intersection of Cantor sets. Well, if the sum of the Hausdorff dimension of these two Cantor sets is less than 1, then the Hausdorff dimension of the difference of them will be less than 1. And on the other side, if the sum of the Hausdorff dimension is bigger than 1, then you can perturb them in order that the arithmetic difference of these Cantor sets contains interval. And in our case, it means homoclinic tangency, or that the frequency of homoclinic tangents is 0. And more than that, and Palis-Balzan work on it, and based on that remark, in order to get that the frequency of hyperbolic to maximum variant set is 1 at the bifurcation, the first bifurcation. And Moreira and Yoccoz prove that there is persistence of tangents and on the other side after some perturbation. So this is relation between fractal dimension and this dynamical feature. But this is a relation. This is related also with this geometric description. And the arithmetic difference is the same as saying projection along this angle of 19 degrees. So if the Hausdorff dimension is less than 1, then the Hausdorff dimension of the projection is less than 1. And on the other side, if it is bigger than 1, then it contains interval persistent after some perturbation. So we are going to give we are going to talk about a geometric description of this kind. Our setting is the following. We have a splitting of such that this has dimension 1. And we would like to understand this kind of geometric description on the stable leaves. But in this case, the horseshoe intercept with this stable leaf is not necessary a product of Cantor sets. So this is a quite different result. On the other side, the weak stable duration has dimension 1, and this will help us. So we would like to base our result on fractal dimension hypothesis. And we will not take yet we will not take the Hausdorff dimension, because the Hausdorff dimension does not vary continuously here. And so we will take a concept on a work by Palis, Viana, and Gugu of upper stable dimension. And I would like to point out this concept of and this work I mentioned is a generalization of the previous work on Palis-Balzan homoclinic bifurcation to a higher dimension. And this upper stable dimension, the fractal dimension we will mention here, is not smaller than the Hausdorff dimension of each stable Cantor set. A stable Cantor set is I'm calling stable Cantor set the intersection of the horseshoe with the stable leaf. It's not smaller, and And in this case, when the weak stable dimension is 1, it varies continuously. So it's a stable criterion for our description. I will introduce this concept now. It's much like the way we calculate how's the dimension of affine Cantor sets, to simplify. You have the horseshoe and Markov partition, and you take advanced iterate of it. And what to do is measure the biggest size inside each iterate. This is iterating in step n, which is here. We call it vertical cylinder. And then we measure the size of each piece with is the interception of this advanced iterate of Markov partition and stable leaf, stable manifold, and we take the biggest of them, which is this DSV here. And then we take this sum, we take this number such that this sum is 1, and we take the limit of this number. This is what we call upper stable dimension. So, analogous to the case I told in dimension 2, if the upper stable dimension is less than 1, then the house dimension of the Cantor set in each leaf is less than 1, so the projection has also house of dimension less than 1 along C1 foliations. But on the other side, a corollary of our work is that if it is bigger than 1, then you can perturb your horseshoe in order that projection along strong stable foliation this contains interval. So it's quite similar to the case in dimension 2. Even though here we are not in a case of product of Cantor sets in the dimension 1.
In what topology, the perturbation?
So a CK. And it's robust also, no? C1 robust. This property. Could do after corollary. And so, this is a consequence of our work. So in order to talk about this consequence, in order to talk about our main work, we must introduce a concept, which is in fact a adaptation of this same concept for a work by Gugu and Yoccoz, and which is the concept of recurring compact set. And in order to introduce this concept, I would like to talk about a renormalization operator we need here. So this picture is the same as I made here. So we take a manifold transversal to the strong stable foliation, and we take the intersection of this manifold with each stable manifold, each local stable manifold. So it will be like a product of an interval and a Cantor set. And this intersection I will call the wall. So this is the wall. And the renormalization operator will enable us to localizate points of the horseshoe. And the definition is the following. You take a point in the wall. So I give an address like this. X is in the interval and theta minus in the Cantor set. And if its strong stable leaf does intercept a piece, then we say that it have a renormalization operator associated to the cylinder of this point. And it's the following. You iterate the strong stable foliation until you are on the scale you are looking to the problem, the local manifold, the scale of the local manifold. And then you project in the wall. So this is the renormalization operator of the x theta minus associated to the cylinder A. So now I can tell what's the adaptation of the recurrent compact set to our case. A subset of the wall is recurrent compact if it's compact, and if for any point in it we have a cylinder such that renormalization operator associated to the cylinder at this point is in the interior of this compact set. So this is definition of recurrent compact set. So if a horseshoe has a recurrent compact set associated to it, we say it's satisfy the recurrent compact criteria. So this is this talk is mainly about recurrent compact set. And I would like first to give a motivation for the recurrent compact set, which is the geometric description of the horseshoe. So the geometric description of the horseshoe is a consequence of the criteria of the recurrent compact set. And this is a geometric description, a blender. And the blender is the following: if you have some leaf, any leaf, C1 close to some strong stable leaf, and if you have any manifold, C1 close to strong stable leaf, with a minimal size, then if it intercepts the unstable manifold of the horseshoe, then you say it is a blender. So it kind of spread the unstable manifold of the horseshoe along the weak stable direction. And this is a consequence of the recurrent compact criterion, which is this theory. And I forgot to know the recurrent compact criteria is robust, so this consequence is robust. So the main theorem is a sufficient criterion to guarantee the recurrent compact criteria, that the recurrent compact criteria is satisfied. And this condition is the one I was mentioned before, is a fractal dimension condition. And if the upper stable dimension is bigger than 1, you can perturb it in the sticky topology such that it will satisfy the recurrent compact criterion C1 stable. So if you want to see blender, you must see which region the upper stable dimension is bigger than 1. So then densely and openly there, you have blenders. So this is the result. I would like to prove a result weaker than a result which is a consequence of recurrent compact criteria, to show how the recurrent compact criteria works in order to give geometric description of the horseshoe. But I will not prove the existence of blenders. I will prove something a little weaker, but easier to and easier to prove. But the heart of the recurrent compact criterion working is in this proof. So we prove that if we have a recurrent compact criterion, then projection along strong stable foliation, and this contains interval. I miswritten there. The projection contains interval. So the proof is the following. So suppose we have a point and the recurrent compact set. This is the point. So as it is in the recurrent compact set, we have a cylinder or renormalization operator associated to some cylinder, such that renormalization operator associated to this cylinder apply to this point, send this point in the interior of the recurrent compact set. So as it's still in the recurrent compact set, then we have another cylinder, the one associated to the renormalization operator, which send we send this point back to the interior compact set again. So we have the cylinder. So strong stable foliation is invariant. So forward iteration of it still intersect the strong stable leaf of the original point. So back into that point, which is the renormalization operator associated to the cylinder A0 of the x theta minus. We have, again, this cylinder, a renormalization operator associated to this, which sends it back to the recurrent compact set, interior of the recurrent compact set. So again, same augment, we have another cylinder. So forward iterates of it is still intersect stable, strong stable leaf of this point. So we are localizing point of the horseshoe here. So we have a point of the horseshoe in the strong stable leaf of this point. So and so this is the proof of the consequence of the recurrent compact criteria. And so I don't know if. So I really would aim to finish the proof of this theorem. This is. Thank you.